Hey guys, this is video 1 of 2 for section 16.4 on Green's theorem. Hopefully if you're watching this video, we have a pretty solid idea of what a vector field is. You've hopefully watched that video, and hopefully we also have a pretty solid idea of what a line integral of a vector field is. Because this section is really just going to give us another technique for dealing with line integrals of two-dimensional vector fields. Now, just as a refresher on how we built up what a line integral of a two-dimensional vector field is, we started out with this idea that we had this sum of scalar line integrals using these differentials dx and dy. Now note, since my bounds here are not an interval, okay, I'm integrating over a curve instead. These are not the dx and dy from my double or triple integrals. These are line integral differentials. And in this case, an alternate way that I could have represented this pdx plus qdy integral is as a dot product, or we could represent that vector differential as dot dr. Now, comment, the reason that I brought this up is I just want to remind you guys of this notation, just to point out, if you see pdx plus qdy, or if you see the vector field pq dotted with this dr differential, these are the same exact thing, okay? So if we're seeing integrals that look like they're expressed in these forms, we can handle them in pretty much the same ways. They are both line integrals representing 2D vector fields. Now, currently, we have a couple ways that we could evaluate that. One, we could evaluate this directly, and what I mean by directly is using a parameterization, right? So I could use some sort of parameterization. We've usually been calling this R of t and doing this on the interval AB. What I mean by evaluating directly, this was the case where we go ahead and we fix my bounds, we fix my function, and we go ahead and fix my differential. Now what I mean by that is this. Recall that for the bounds, we're trying to rewrite this as a regular Calc 1 type problem, so I'm going to integrate over AB instead of this curve. To fix my function, well, whatever vector field you're integrating over, substitute in your parameterization to get rid of your x's and y's and replace them with just the single variable t. And then for your differential, we're going to express dot dr on the end as dot r prime of t dt. Okay, so by the end of that, you should get a single variable integral. The alternate method that we have for expressing this, currently we have the fundamental theorem of line integrals. Now, that only applies if this PQ vector field is conservative. If you don't remember what I mean by fundamental theorem of line integrals, well, here, this is that case that we've got this formula where you take this line integral of a gradient, and you can express this as basically, if I could spell this out in order, basically what happens if you take that potential function and you evaluate it on the endpoints, right? So when I say f of r of b and f of r of a here, we're dealing with the same exact parameterization or type of parameterization we had before for a curve. R of B just means where C ends, and R of A just means where C starts, okay? So this is an alternate way that we could evaluate if we have a conservative vector field. Now, that's a recap of where we're at thus far. What I want to go from here is this. If we don't necessarily have a gradient, the fundamental theorem of line integrals doesn't help us, and we've already seen that sometimes doing this the direct way can get really messy really fast. So, if we have a vector field that's not necessarily a gradient, are there other shortcuts for doing this? Well, I wouldn't be asking this if the answer wasn't yes. So yeah, there are shortcuts. We're going to cover a very specific shortcut though. So this section on Green's theorem, this is going to cover the following case. We are looking for where this curve that we are integrating over meets three criteria. Now, I need to spell out for you guys what these criteria are. One of them we've seen before, okay? C is closed. So if you've got some sort of a curve that forms a loop, what I mean by closed is it starts and ends in the same place. Okay, so you notice every single one of these that I'm drawing here, they start and end in the same place. So whether or not they cross themselves or not, you notice all of these things form a loop. Okay, so pretty much every single one of these guys is going to be, if I can spell that right, closed, but, you know, things like this or this guy or this, you'll notice they start and end in different places, so pretty much every single one of these that I just drew over here, these guys are not closed. Okay? Now, the other criteria that we need on this curve C that we'll be integrating over for the shortcut is that we need C to be simple. What I mean by simple is that my curve cannot cross itself. So, you know, if I want some examples of simple curves, you know, something like this guy also counts as simple. You know, you could get really, really messy here. These guys, pretty much every single one that I just drew here, these are all simple. On the other hand, if you have a curve that crosses itself in any sort of manner, be it closed or not, these guys are all not simple. Okay? And then finally, the last of the criteria that we're going to need for the types of line integrals that we're investigating, we also need these curves that we're integrating over to be positively oriented. What I mean by positively oriented is that I need these curves to run counterclockwise. Now, for me to specify counterclockwise or clockwise, I kind of am assuming that I'm dealing with a closed curve. So for pretty much every example that I'm drawing here, you know, stuff like these guys are going to be positively oriented. Whereas, on the other hand, if you go in the opposite direction here, if it looks like your curve is running clockwise instead, these guys are going to be not positively oriented. You know, you could say negatively oriented. Or you could say not positive. Either way, similar kind of thing. I'll go ahead and make the comment here for this last example about these positively oriented curves. If you're looking at some sort of a curve, you know, it can be kind of messy. You know, we've already seen that I could do these like really crazy, like squiggly looking borders here. Maybe it might be kind of intuitive to you guys whether or not we have something that's got a positive orientation versus a negative orientation. What I'd like to suggest is kind of this following trick here. Think about if you have a little person that's walking around the boundary of this curve, and what I'm going to go ahead and do is I'll think about this person, I'll move them so that they're touching one of the, you know, they're touching along the curve as they walk around it, right? Let's, you know, kind of view this as like a fence that you're walking around. If these guys are walking around this enclosed region by this fence, touching this, if you are following the direction of the curve, this thing is going to be positively oriented if you can trace that fence touching it with your left hand while walking around. Now, on the other hand, if this thing is negatively oriented, for you to, you know, walk around on the outside and trace along, you know, the fence, grabbing onto the fence as you walk around outside of your region, you know, you'd have to face the opposite direction. You'd be grabbing that fence with your right hand, right? So think about walking around the outside of your region, you know, kind of grabbing along the fence as you go. Are you grabbing it with your left hand or your right as you follow the curve? If you're grabbing it with your left hand, you're positively oriented, okay? Now, with all of that said, again, the types of integrals that I am going to be looking at shortcuts for need to have all three of these criteria. So I need to have a loop. It can't cross itself, and I have to be running counterclockwise along this thing. Now, if I do have all those criteria for this curve that I'm taking a 2D vector field line integral over, what's my shortcut? Well, I'm going to jump right to it. Your shortcut is called Green's theorem. Now, how Green's theorem works is this. I'm going to go ahead and assume that we've got that positively oriented, simple closed curve. I'll add in an additional assumption that it's piecewise smooth. What that basically means is anything that I would give you guys in this class, it's differentiable. That's kind of what smooth means. You know, if C meets these criteria, well, if C meets all that criteria, there's going to be some sort of region inside of your curve. I'm going to call that region D. Now, if the functions that form up your vector field, P and Q here, if those guys have continuous partials on some sort of region, you know, containing D, then we get this expression right here. Okay, so I'm going to go ahead and box this because this is the formula that we're going to keep coming back to here. This is going to be important for us. Okay, so I'll box this. Now, again, I do want to emphasize this is not necessarily the only way that you are going to run into this formula. You could also see it expressed in this manner. We are working with two-dimensional vector fields here, so whether you see this as pdx plus qdy or pq dot dr, you know, these are going to give you basically the same thing. Okay, so both of these expressions represent the same vector field line integral on the left-hand side. We can rewrite these in terms of double integrals instead. Now, before I jump into the meat of how to use this theorem or, you know, examples or why it works or anything like that, I'll get a couple bitty things out of the way first. First off, I'm going to mention some notational variants here. In this section, you're potentially going to start seeing symbols that look like maybe this or this. They'll sometimes pop up in the textbook or in your homework, or you know, if you're a person that likes to use other sources to back up the information that you're getting in this class, sometimes you'll see these symbols for your integral symbol instead of this thing. Okay? Now, that doesn't necessarily mean anything particularly fancy. It's just an alternate way to represent your line integral. But when you do use one of those symbols, you are suggesting that the curve that you are integrating over is closed and positively oriented. Okay, so we've got one of these loops that's running counterclockwise and doesn't cross itself. Another comment that I'll go ahead and make about notational variants, particularly if you're using other sources, is that whenever you see one of these little D-looking symbols, kind of like the ones when we use partial derivatives, you know, sort of like up here. If you see one of these little delta, like D symbols, if you see that not in a derivative notation, like here, if you see it in front of a set instead, what that symbol means is you're talking about the boundary of that set. So since in this theorem, I noted that C is this curve and C kind of encloses this two-dimensional region D, an alternate way to represent that is if you look at the boundary of that 2D region D, it's a curve. Okay, so some sources, instead of, you know, calling these C and D, they might call this boundary of D and D, and it really means the same thing. Now, another note that I'm going to get out of the way here is, you know, what's kind of the point of this? What am I really doing with this formula that I've boxed where I'm converting, you know, this line integral to this double integral? Well, point is, we can rewrite a line integral as a double integral. You know, instead of rewriting my bounds and my function and my differential, we've kind of got a different way that we can approach rewriting my bounds, my function, and my differential. We're just interpreting this as a totally different kind of integral is what we're starting with. And what this theorem does is it makes a connection between the behavior of that boundary curve and what's going on the region inside of that boundary curve. Now, it's kind of a bit of a strange example here. I'm going to go ahead and pull up sort of an old-timey reference here that makes use of this theorem. I don't know if you've ever seen one of these doodles. This thing is called a planimeter. And what's happening is you start off by centering this thing over a curve that you want to trace, and then you zero out on this device, so you can start out at 0. And what this guy's doing is he's using this end piece to trace along the boundary of the curve. In a sense, kind of like what we're doing with our integrals, he's tracking what's going on with the C that bounds that region. And ultimately what this device does is there's this meter down here that, based off of you tracing that curve, it tells you what the area is inside of that. Now, if you're wondering why the heck you would care about a device like this, this was sort of a old way that people used to, you get a map, you trace out this region, it would tell you the area inside, and if you were worried about surveying or, figuring out information on your, property, how much land you have based on some sort of map region, that's what this device was used for. Now, again, why this relates to what we're doing now is if you actually look up, one of these objects and try to figure out how the hell does that work, right? You trace the little curve that goes around the outside, and then it spits out the area magically somehow. Well, what's really going on is if you look down at the mathematical derivation here, there's this section right here where we link a line integral to an area integral, right? A double integral. This is Green's theorem, okay? This thing works by Green's theorem. It's connecting the behavior of what's happening with that curve to what's going on with the area inside of it. And maybe you're kind of brushing this off like, oh, that's an old-timey thing, like, why do I care? This is actually still something that can be used for surveying. It's just that we've updated the way that we use it, right? Instead of actually getting a physical hard copy of a map, you can pull up something using GPS coordinates, drop a bunch of pins to point out the boundary of this curve, and it'll tell you the area of the region. So surveying methods still use basically Green's theorem to accomplish these techniques. So this is just one of the applications that we have of this theorem. Now, with that all out of the way, why the hell does this work? Right? I just dropped this formula on you guys here. So my ultimate goal here is, again, that if I've got this line integral, p dx plus q dy, I want to show that this could be represented as this double integral, dq dx minus dp dy. Why does that work? A fair warning, if you're not a person that gives a crap about derivations, we're going to work on this for a hot minute. There is an example at the end of this video. You might just be interested in skipping ahead to that, so we'll save you a little bit of time there. But if you want to know why it works, or at least get a feel for what we're doing here, feel free to go ahead and keep watching. Now, if I want to ultimately show why Green's theorem works or what's going on here, the formal proof of this, if you're looking at the broadest, most general case, it's tedious, it's long. I'm going to simplify this and just look at a subcase so we can kind of get a feel for the general argument where this is coming from. If you want to show that this formula works, we need to show two pieces, right? What I'm going to link here is this pdx and minus dp dy part, and this q dy and this dq dx part. Those are the things that I want to link here. So I could treat both of these guys separately. With that said, the argument that you use to set up showing one of these is pretty similar to the argument that you used to set up the other. It's the same sort of technique, so I'm not going to do it twice. We're just going to look at one case, right? So I will go ahead and make the observation here. You know, both cases are similar. I'll just focus on this one, right? We'll just do this guy first. Now, if I'm looking at that case, I am going to start with this right-hand side, okay? Already got the right-hand side written out. Maybe let me just spell out, hey, we're integrating over D here. What D am I integrating over? Well, I'm going to go ahead and assume that I've got this type 1 region right here. Okay, so I will go ahead and suppose D looks a lot like the following. Now, I've got this region D, since I've said that it is type 1, so I'll go ahead and actually spell this out here. It looks like my type 1 case. What I mean by type 1, when we were dealing with double integrals, that was where you had a top curve and a bottom curve. So I've got that, right? We've got a top curve, you know, pointed this way, a bottom curve pointed this way. I'll go ahead and assume that I actually have functions to describe both of these things, so we'll call that G1, and here the function that I'll use to describe this guy, we'll call this G2. The way that I've set this up, your usual cheater orientation for parameterizing curves as you go in direction of increasing t. So you'll notice that I actually set these up so both of these segments point left to right. That actually doesn't give me a curve that is positively oriented all the way around this D, so I'll go ahead and make the observation that if I set this up with my usual cheater parameterization for both of these curve segments, this overall curve C that goes around the whole thing positively oriented, it's going to go in the same direction as C2, but the opposite direction of C1. So, if I set up C2 minus C1, that's going to be a positively oriented, simple, closed curve. Okay, so we've got this thing positively oriented, check mark there. This is simple because it doesn't cross itself, and it is closed because it does not form a loop. So, got the setup initially described. Let's worry about why the heck these algebraic expressions come out the same way. Well, first thing I'm going to do after starting off with that right-hand side is I'm going to actually write out this integral in terms of, you know, dy, and I've used this variable t over here, and dt, and actually put some bounds down on this, okay? So if I set that up, you know, my integrand, I'm not doing anything with it yet, I'm just setting up my bounds. If I do this as type 1, that means y is stuck between two functions, so we want to integrate with respect to that one first. The way that I have this set up, the top function is g1, so I'll put my g1 of t up here, and my bottom function is g2, so I'll put my g2 of t down here. If you're looking at bounds on t, t is kind of like where we would usually put the x-axis. T here is stuck between a and b, so that's the integral that we have to worry about taking. Now, as far as evaluating this thing, we want to work from the inside out, so that means the outside of this integral, we are not really going to do crap with that yet. I'm just going to leave that be. Now, what you would have to do is antiderive the inside with respect to y first. Well, this thing kind of looked like a derivative with respect to y, and I'm anti-deriving with respect to y. Hopefully we get the idea that that's going to give you kind of the original function, you know, after saving this negative sign. So I should expect to get the function p back. Now, catch, just writing this as minus p, you know, evaluated between these two curves, that's maybe not the most descriptive. So instead of just writing this with the function variable, I'm also going to note the input variables that we're using at the same time. Here, the input variables for p, these are going to be t and y, okay? That's how I've set up this particular expression. We are using t and y. So anti-deriving dp dy, you get p, but p is a function of t and y here, okay? So that is what we need to evaluate this at, okay? We are substituting in y equals g1 of t and g2 of t to that expression. So I'm going to go ahead and do that, right? If we already noted that we substitute these in for y, well, y is the second component. That means if you plug the top bound in, you're only doing it for the y component. So here goes my g1 of t that I had to substitute in. And then I have to subtract off what happens when I plug in the bottom. Well, your negative signs are going to cancel. And you are going to get a t comma g2 here. Okay? Now, after I have substituted these in, this is maybe going to be kind of a trivial looking step. What I'm going to do to make the jump here is I'm just going to do a little bit of rearranging. I'm not actually doing anything significant here. I'm just going to split this integral into two pieces. You know, I've got a sum here, and I'm also going to rearrange this. So, you know, if you think of this as the first part and the second part, I'm just going to change the order up. So I will have this second part, I'll write that first. I said I would split the integral. Now, the first part, I'm going to write this second. Actually, we'll change this so that instead of summing this, I'm subtracting here. Okay, so first part, writing this second. So same expression as I have up top, it's just reordered a little bit. That's all that I'm doing. Now, for this next part, this might be a little bit of a logical jump, so I'll leave myself some space here in the middle to explain what's happening here. What's really going on is this first integral. This is really a line integral for p dx, and this part over here is really a line integral for p dx, but over a different curve. Now, where did that come from? I'll go ahead and make the observation that y'all are probably not used to doing this in this order, where we jump from this statement to this one. What y'all should be used to at this point now, though, is going in the opposite direction, right? Now, whenever I go ahead and try to evaluate a line integral, I've told you guys that we have to fix my bounds, we have to fix my function, and we have to fix my differential. Now, notice what's happening here is I am assuming the parameterization. Let's say I try r1 of t. I'm trying the parameterization t comma g2 of t. And I'm doing this parameterization on the interval from A to B. Now, again, y'all are used to kind of going backwards here. If I had started down at the bottom and I wanted to fix my bounds, we have to steal the interval from the parameterization. If I want to fix my function, I have to plug my parameterization into it. And if I want to fix, my differential here, what we would usually do for replacing dx is you basically just take your x coordinate of your parameterization and you derive it and slap a t on the end. Well, if you derive t, you get 1. And that means if you slap a dt on the end of that, all that you're doing is just replacing dx with dt in this particular case. And we're doing pretty much the same exact thing over here, except for it's a slightly different parameterization for, let me get my numbers straight here. It's a slightly different parameterization because we're dealing with the other curve. Okay, so for this one, the parameterization that we are using is t g1 of t, and we're doing this on the same interval. And again, just to reiterate, you know, where are these, like, what are these coming from? Well, if I was dealing with the G2 curve over here, and I scroll back up and look at my picture, my G2 curve is this thing that's on the bottom. Okay, so every single point on that curve looks like t, okay, whatever input t you plug in, comma, whatever happens when you plug that in, so G2 of t. Okay, this is where my cheapo parameterization came in. Okay, if I parameterize that curve in the most direct way possible on the interval from A to B, I get C2 back. And if I parameterize C1, you know, I'm doing the same thing with this G1 curve. Now, final comment that I'll go ahead and make is I just want to consolidate these into one piece. And if you think about what's happening here, right? I'm really integrating the same function. It's just that here I'm integrating over C2, and here I'm basically going in the opposite direction because of this minus sign. I'm going in the opposite direction of my C1. Now, a way that I could express this just with combining those curves is maybe I could think about going along C2 and then going in the opposite direction of C1. But let's one more time take a look at my picture. If I trace out C2 and then go in the opposite direction of C1, this is that curve C that we were trying to integrate over in the first place. Okay, so this guy is my PDX that I wanted, right? You know, the overall whole goal in the first place is we were just focusing on this very first case where I start out with that right-hand side and I wanted to get to integral of PDX. Okay, and we got there. Now, I did say that was only part of the proof. If you want to extend this thing, there's a couple details that you need to worry about. First off, the book, when they split up their argument for this, they worked this problem over a slightly more complicated looking region. Now for us, my G1 and G2 actually intersected at a point. For the book setup, they don't necessarily have that happen. So these might have these little vertical chunks over here so that actually if you wanted to set up your, you know, C1, C2 for this region, you know, you would be getting, instead of just 2 pieces, you have to worry about 4. So these vertical sides, what happens there? Well, spoiler, I'm not going to bother with the details. Along those additional boundary curves, you're going to get a 0 integral back. And hopefully that kind of makes sense, because since we were doing a dx integral here on those vertical regions, there's no change in x. You're on a vertical line. So your change in x is 0. You're going to get a 0 integral back. Key point for observation to extend this proof: if you add in those little vertical segments because your curves don't meet at your endpoints, it doesn't change your result. Okay, so we still end up with the PDX integral over C that we had before. Another comment to extend this proof: we don't necessarily have to assume that we've got this working in some sort of type 1 region. You know, if I've got some sort of a region, let's say that this thing, you know, can't just be expressed with a top curve and a bottom curve. Well, what you want to do then is you can cut this thing into pieces, right? So instead of just having this one big C curve, what I could do is think about cutting this up until I do have a bunch of type 1 regions. So you notice here, I can think about this guy as being a top and bottom curve for, you know, region 1. I can think about this as being a top and bottom curve for region 2. And I can think about, let me get the direction going straight here. I can think about there as being a top and a bottom curve for region 3. Okay, so what you would want to do is, once you decompose this, think about setting up 3 different integrals. right? So we'll basically get an integral for each region. Okay, and a comment, sorry about that. If you're tracing one of these regions, you'll notice that here for D1, I kind of have the section that goes upwards if I were to trace around D1. But if I have D3 here, I'd have to go in the opposite direction to trace around D3, and in the opposite direction to trace around D2. Those sections where your curve, points in the opposite direction of each other, when you add up all of the integrals for these regions, the line integrals along those pieces are going to cancel out. So even if you decompose this and you're kind of worried about the boundaries mushing together where they touch, all those places where you made additional slices, they'll cancel each other out. So if you don't have a type 1 region, if you have something that's more complicated than that, it's okay. We can break it apart. And then the final step in the proof, I mentioned that there were kind of the two things that we needed to show. We only focused on the P part of the equation. If you're worried about this Q portion of the equation, we're basically doing a similar problem, but flipped on its side, right? So for us, we had a top and bottom function specified by, the C1 and C2 curves. Here you're going to have a right and a left function specified by, I'm using the same labels, the C1 and C2 curves. Now, a catch in case you were wondering why there's a weird negative sign in Green's theorem, before the previous case, the one that we just did where I had a C1 and a C2 curve. Remember, when we went to try to form the overall C curve, we had to go in the same direction as C2, but the opposite direction of C1. Okay, so my C ended up being C2 minus C1. Now, the reason that I drew these pointed in this direction is that my usual parameterization, this guy is in my direction of increasing T, and what that's going to give me here is, as T gets bigger, my arrows will point to the right. Now the catch is, if you look at this expression where we did C2 minus C1, this is not the way that we set up area integrals, right? C2 minus C1, that's your bottom function minus your top function. So this is the opposite of my usual area setup. Now on the other hand, over here where I've got this C1 and C2 curve, again, your usual parameterization for these curves goes in direction of increasing T. Here for this setup, you're going to use T and X instead, because both of these are functions of Y. So if I'm using this C1, travel in the opposite direction, C2 to build my C, the usual parameterization that we would get for that is actually in the same direction of how we would usually do area setup, right? So this guy's in the same direction as area setup. Because when you try to find areas of regions, you do right minus left if it's a type 2 region. And that's exactly what we have here. So comment, if you're wondering kind of why we got that negative sign, when we just did this, this is why. If you're wondering why the dq dx in the formula doesn't have a negative sign, this is why. It basically aligns so that we're trying to correct off a sign error in the case that we just did. Now, with all that said, if you are not a person that really cares about the derivation of things, if you just want to know how to use the formula to do the problems, here's where we tune back in, right? So again, what we just got, okay, what we just proved is Green's theorem. It's probably been a while, so maybe we might want a reminder on the formula. The formula for Green's theorem says that if you have P dx plus Q dy, if we're taking that as a line integral, we can rewrite this as an area integral. And that area integral is going to be dq dx minus dp dy. over whatever region that's C enclosed. Okay, so this is what I'm trying to get us to use here. So, how does this work in practice, right? Well, for one, I need to get a feel for what my curve is. Well, here I've just said C is this curve that's bounding D below. That curve, whatever region that's bounding, that's going to be the area that we'll be integrating over. Now, if you know what area you're integrating over, another handy thing to figure out would be what your new integrand is. And your integrand basically comes from whatever vector field you initially started working with in the first place, right? So here, for us, this equation or this expression that I'm starting with in the first place, please be careful. I mentioned whether you write this in vector form, pq.dr, or if you write this in, the scalar form, pdx plus qdy, your p function in this formula, this is going to be the function that's attached to dx, and q is going to be the function that's attached to dy. So occasionally you'll see a textbook or a homework set or a problem try to pull a fast one on you. If you look really carefully, I actually have the dx and dy integrals ordered backwards here. So step one that I'm going to do is make sure that this is written in the right order, right? So here, if this guy is the thing that I'm integrating over, I want the dx one first, so minus y squared dx. And then I want the dy one second, so plus x, y, dy. And again, the whole point of that is the thing attached to dx is your p, and the thing that is attached to the dy is your q. So now we just want to directly apply the formula. What the formula says is that here we should be able to express this as dq dx first. So what's dq dx? That's my derivative of the second piece with respect to x. You will get y. And then I have to subtract off whatever happens when I take the derivative of p with respect to y. Well, that's going to be minus 2y. Okay? Now, again, just to reiterate, here is my dq dx, and here is my dp dy. So this is just me straight up applying Green's formula or Green's theorem right here. Okay? Now after this, the thing that you would need to worry about is, well, first off, simplifying. I'll go ahead and note this is really 3y dA that I'm worried about. And from here, I just need to set up an area integral. Now, I've said that we're integrating over D. Well, that's all well and good, but if I antiderive 3y, what the heck am I plugging in? Heck, what am I antideriving with respect to first? I need to go back and take a look at this region, right? So what region do I have here? Now, some points about this region. One, if I have this top curve and this bottom curve, I can interpret this as a type 1 region, okay, top minus bottom. That means I'm worried about what these curves actually are. So here, this is, it goes from 0, 0 to 1, 1. It's got a y-intercept of 0 and a slope of 1. This is hopefully recognizable as the y equals x curve. And on the bottom, since this is the y-axis, this is the y equals 0 curve. Those are going to be your bounds on y. If you're looking at your bounds on x, how far to the left and right does your region go? Well, we've got that this thing starts at the origin, so here's x equals 0, and it stops at this vertical line, x equals 1. So here are my left and right bounds. Okay, so what that's going to suggest for me here is we'll integrate with respect to y first, going from 0 to x, and we'll integrate with respect to x second, going from 0 to 1. Okay, if I go ahead and actually crank through that, you antiderive with respect to y first. I'll get 3/2 y squared, evaluated between y is 0 and y is x. And then I actually substitute in those bounds, so I'll get 3/2 x squared minus 0. And now I can go ahead and antiderive with respect to x to close. Okay, so this will basically be 3/2 x cubed over 3, or just the 3's cancel, you get x cubed over 2. Evaluated between 0 and 1, well, we're going to get a half back for this guy. Okay. A point that I should probably highlight here, I did kind of play this down a little bit in setting up this problem just because I was trying to give you a rudimentary example. If you're worried about checking your hypotheses, like I said, I tried to give us a rudimentary example where we didn't have a lot of frills going on. This is a simple curve, doesn't cross itself, going around my region. It's a closed curve. It does enclose a region. It is positively oriented, so it is kind of traveling counterclockwise around my region. This is going to be a fitting case where we apply Green's theorem here. This is why, aside from sorting out what my dx and dy was, we just went straight through, right? Rewrite your integral, actually remember how to set up a double integral and evaluate. Now, for this next lesson, okay, video part 2, spoilers on what we're going to look at. What are some tricks that we might have to keep an eye out for? Things like orientation or other things that will pop up in my setup, okay? So if you want more examples than just this one, check out video 2.